Howdy again, everybody. In this video, we're going to chat about our Unit 3 pieces that we'll be going through. So magnetism at that really high level view. So we're going to parallel it very similarly to what we did in electrostatics and a little bit parallel in circuits, where once we find some of these pieces where we invent a new circuit component, we'll revisit and add in that new circuit component and look at some of the behavior. Admittedly, not a lot, because there's so much that we can do in magnetism. Really, this is why, like, as a physics major, I took an intro physics class for E&M, kind of like this, and then there was a second, so intermediate E&M, and then a third advanced E&M, and then even after that, there was still graduate E&M1 and graduate E&M2, and there's still more E&Ms than even that. Things we cover in also special relativities and general relativities, modern physics kinds of pieces, and further in other research. And there's still active areas of research going on in a lot of this electrodynamic kind of behavior. We are really just dipping our toes into electricity and magnetism in this course. And it's funny that we say we're just dipping our toes in, because we are doing a lot. There's a lot that we're going to, at some level, cover, and at some level delve deep into. And it's just sort of, on at what scale and what timeline makes sense for us. We will do as much as we can in the time that we have together. And we will always, of course, focus on the learning objectives that we have to cover for the guaranteed transfer within the state of Colorado. But it's generally the same kinds of things that hopefully should transfer anywhere in the country, or at the absolute worst case, you'll have a very strong foundation when you retake this class, if you have to retake the class at your 4 year. Typically, that's more summer students that end up in that case for various reasons. But I will even say I took this class effectively 3 times as an undergrad. I took the algebra-based physics, but I took it at the same time as I was taking calculus, so I sort of got both layers. And then I took the calc-based physics, and then I took the this class, but at School of Mines, and sort of that repeated layers. Like, I learned something new each time, and I've been taught this class. This is probably at the time of this recording in the year of our Lord 2025. This is probably like the 20th or so time that I've taught or learned, or maybe even 30th if I include all of the other pieces that I've taught, learned, done things with E&M. I'm still learning and appreciating new layers of things. Like, it's a dense subject. Let that excite you, and don't let that overwhelm you too much, because this is a deep, deep, deep ocean of content that we're wrestling with. But we can grasp big swaths of it, especially if we recognize, again, as I started this video, that parallels that we see with magnetism and electrostatics. So let's get into it. If we're talking more about some of those parallels here, so back in electrostatics, we talked about these fields, right? These E fields, and those were the source of a force. This secretly had a name that I may or may not delve into. I don't think I did in the previous high altitude videos, but in the actual videos, I think I will, as we go through in the deeper detail, the deep dives on those. This is part of the so-called Lorentz force law. The other part is the missing part from magnetism, where really it's E times this V cross B, where this is the velocity of the particle cross-producted into this so-called magnetic force. So there's sort of these two terms, this QE term and this Q times V cross B, if we use that distributive property here. This is the total Lorentz force law equation. And because the forces are so similar, well, then we might ask the question, how we generated E fields by saying, I have like a point charge does a K times a Q divided by an R squared times an R hat. We end up seeing a very similar rule for how B fields are made. It ends up having this over R squared rule. I'm going to write this one in terms of 1 over 4 pi epsilon naught instead of as K, because it's going to better mirror what happens over here, where there's a mu naught in the denominator. And there's going to be, again, a Q factor in the numerator and an R hat in the numerator. But there's also this weird thing, whereas you have to do like a Q times V crossed with R hat. And then this becomes like really a V hat in order to make the units work. I think, I could be wrong on that. I almost never write it in this equation because it's so rare. And even if we do have it, it's such a small B field made by a single moving charge. So what often happens instead is we talk about, okay, in the similar way that a small piece of E field was made by a small charge divided by 4 pi epsilon naught, aka k, times r squared times r hat. And then we added all of those up to find the total electric field made by that distribution of charges that we separated. We do the same kind of thing where we say, hey, a B field is made by adding up small pieces of magnetic fields, which look like a mu naught over 4 pi. Sorry, I guess the mu naught should have been in the numerator up here. Mu naught over 4 pi times I dl crossed with r hat all over r squared. And then we integrate those pieces. And this is what we call the so-called BS law, the Biot-Savart law. But I mean, it's the BS law because look at it. But at some level, it is really similar. We see this piece where it's some fundamental constants. We see this piece that looks like a source term based on moving charges, in this case, current. It's tied in this weird right-hand rule play. This is where we see one of those differences with that r hat. But we also see, that r hat vector, that observation piece matters. And then we also see they're both inverse square laws. They both have this 1 over r squared piece. And so by looking at some of those parallels of similarities with the Coulomb's law and the Biot-Savart law, we're going to get some better intuition and practice with some common geometries of how we find wires carrying charges and building the electric or B fields from those kinds of pieces. And we'll also revisit right-hand rule stuff for both finding the directions of magnetic fields, for finding the direction of magnetic forces on charged particles moving through magnetic fields. We'll also, in the same way that we exploited symmetry conditions with Gauss's law to help us find E fields in certain situations, there's going to be a similar thing, Ampere's law, where it looks similar on a superficial level, where, hey, if I'm adding up E field through some sort of closed surface, and it has to equal the charge enclosed divided by epsilon naught, in a really analogous way, but a dimension lower, instead of it being divergence theorem, it's going to be Stokes's theorem. So this time we're adding up the B field as it goes around a closed loop that we draw, and it has to equal the current that goes through that loop times mu naught in this case. And we'll see some of those similar kinds of things and similar symmetry conditions that we use to exploit to help us to understand integrals that would be hard to do for these, but are still really common geometries. For instance, if I just had an infinitely long segment of current carrying wire, this is a really hard problem to do because I'm going to have to integrate from negative infinity to infinity, break up all of these small segments of the wire that carry a current along this place, and then find an individual R vector and then normalize it and then throw this in here. It becomes a really nasty integral to build and to solve. But it becomes basically 2 lines of algebra when we use this to figure out that, oh, it's going to be mu naught times I divided by 2 pi r, because at some level this left-hand side is going to reduce down to just the B field times the length of the Amperian loop that we draw. And what we're going to find is that the B field curls around the wire like this. And so we're going to draw our loop curling around like this, making the dot product all go away, and we just get times a 2 pi r as the length of that loop. And then because all of the current goes through it, it's just mu naught times I divided over. Again, like 2 lines of algebra to figure out the B field of an infinite wire using this equation that lets us take into account the symmetry of some of these highly symmetric cases in the universe that represent a pretty common situation, a relatively long straight wire, or at least as we're relatively close to a straight segment of wire, this equation is going to be really effective at modeling the strength of that magnetic field. And we'll get more and more practice with some of those pieces, when we can use them, when we can't use them, how to use them when we can, all those kinds of pieces. This is, again, just that quick set of here's what we're going to encounter and what we're going to delve into much more detail with later. So we've talked a lot about sources of B field right now, and also, the force on some of the B field pieces. There are other pieces that we're going to get into then with now that we know where magnetic fields come from, we're going to be like, hey, magnetic fields and electric fields seem to sort of interact in some of these ways based on some experiments that we run. And we run into a new Maxwell equation, the so-called Faraday's law of induction, where essentially if I have a loop here and there's a magnetic field going through that loop, but a moment later, that magnetic field weakens. There is a change in the magnetic flux through that loop. And because of that change in magnetic flux, there's going to be an induced current around the edge here. And to find the direction of this, we use a thing called Lenz's law, which I'm just going to do in my head real quick. So the B field is going up, and then it's going down. So the change, or it's decreasing. So the change is down. I oppose the direction of the change, and then my thumb is telling me, and the way my fingers curl around my thumb is telling me that I would get current going this way, compared to if I increased the current, or increased the B field, sorry, I would actually get current going in the opposite direction. It would go this kind of a way in the loop. And what that means is, well, where did that current come from? Eventually we find out that it comes from when this B field changes, there's an electric field that swirls around that change in a particular way. And that happens to drive a current because there's a conductor there, and that conductor is able to move charges around if there's a reason for those charges to move. And that means we get this non-conservative voltage. Everything else, if we went around in a loop, we ended up with a change in voltage of 0. But here, if the E field that gets induced is always curling around, it's a fundamentally different kind of electric field where we do pick up a non-zero voltage by traveling in a loop. And so we learn about some of those new rules and implications there, and a lot of the nuance there. We'll spend a long time with these pieces because induction is such this dense and honestly really interesting topic. This is how generators work. This is how electric motors work. This is how basically anything super cool, induction stovetops. This is how, this is the thing that most of our modern world is built around. And from there, we'll also talk about, because of this law of induction, there's circuit elements called inductors, where if you change the amount of current through themselves, so typically we think of a coil as an inductor, if I have a current flowing through this thing, it's going to create a magnetic field through itself. But if I then change that current to have more of it, there's going to be more of a magnetic field through itself, and then that magnetic field change, because the magnetic field change, it induces an EMF, electromotive force. It's another word for a voltage. Which is of course annoying because voltage is not a force, and EMF has the word force in it. It's sort of a historical, archaic artifact, but it's important that we use some of the language of the field, even if it's not technically correct. And I think it also preserves a little bit of that humility. We don't always know what we're dealing with when we learn any new thing, when we're exploring things, when we're researching stuff, and we have hypotheses and theories about how the world works. And it turns out that many of them don't end up panning out. They might be a close approximation or a good model, but they don't really reflect what it is. Like, for instance, the gravitational force is, as far as we understand, not really a force in the same way that other forces are, like the electromagnetic forces. These are real forces, as far as we can tell in the model that like Isaac Newton built, versus gravity appears not to be. So we'll learn about these inductor properties, how they work in circuits, how they work with resistors, how they work with capacitors, how they all kind of work together. We'll talk about some applications, and admittedly, a lot of that work is going to be very surface level, very like not super in depth, and that's partially because of how much other content we have to cover in this class. It's partially to do with the amount of math that we currently have exposure to. And there are probably going to be some extra credit opportunities if people want to go above and beyond, especially if they have those other classes done either co-requisitely or prerequisitely, and they're looking to explore some of those applications. I'm happy to do some individual work or with groups that want to do some of those pieces. And from there, that's pretty much the set of stuff that we're going to have go into our Unit 3 and Exam 3 kinds of stuff. So after that, we really get into this transition of now that we know about magnetic fields, we know about electric fields, and we've seen a little bit about how magnetic fields create electric fields. And at the end, we come across a very special case where it looks like, for instance, I'll show you the case right now, actually. If I look in a capacitor while it's charging, there's current, actual current flowing like this in order to make positives appear here and negatives appear here. We have to take positives away by having this current flow down, current being the flow of positive charges by convention, even though it's actually the negative charges that are moving in the opposite direction, which gets into a good point. We'll also talk about this thing called, just blanked my mind. It's called the Hall effect, which is how we finally figure out after 100 years of doing circuit analysis kinds of stuff as humanity, we figure out that, oh, Ben Franklin is actually wrong in setting this definition, this precedent of current being the flow of positive charges. It appears that in essentially every case, it's actually negative charges flowing in the opposite direction that we thought the positive charges were flowing in. And it's rare that you get a case like the Hall effect demonstrates, where basically they took a metal block and they put a positive and negative attached to it to make current flow this way, conventional current flow flowing this way. And they put a magnet, so like a north here and a south over here. And what they find is that if you had a conventional current flowing this way, you're going to end up with positive charges up here and negative charges down here. But if it was negative charges flowing the opposite way, you would actually get the opposite effect, positives here, negatives here, like flip-flopped. And so if you measured the voltage, this is the experiment that they run, from end to end on these ends of the metal bars, you do this, you'll get a negative reading if Benjamin Franklin's wrong, and you'll get a positive reading if he's right. And it turns out we get a negative reading, which is how we sort of understand that conventional current is actually the flow of positive charges. But anyways, if I'm applying this Ampere's law piece and I'm trying to find the magnetic field, like right here, everything works fine. I have actual current going through this loop I draw. And the same thing over here. If I draw it here, I get current flowing through here. But if I draw this loop with a surface like this, but I make the surface go kind of through here instead in this weird like plastic bag that's really hard to draw, and I'm not going to worry about it too much. But even weirder, if you looked at, I do it right here and everything's fine, and I do it right here and everything's fine. But if I did it in between the plates, we still measure a magnetic field, and it follows all the same properties, but there's no actual current moving between here. This is empty space. So there has to be something else progressing in this area. And what we find that is just like we had changing magnetic fields create changing electric fields, it turns out that the changing electric field, as I dump more charges on here, the E field gets stronger and stronger and stronger. And that changing electric field creates a changing magnetic field that wraps around it. And that leads us into this free charge solution that we'll talk about in Unit 4, where if there's no charges in the universe, it's just empty space, it's still possible for there to be changing magnetic fields that create changing electric fields that create changing magnetic fields forever and ever and ever. And that's what we call light. So that's what we end up talking about: lights, waves, optics, all of those fun phenomenon that I'll talk about briefly in the next video, because we won't spend as much time on waves because of the detail. We don't have the time necessarily to do so. And this E&M class, like I said, this is what the electromagnetism and waves in particular, dynamics. That's why there tends to be so many classes associated with this. This first one is really just this big survey of electromagnetism, where we get to have fun math tools. Everything we did in Phys 1, everything we've done in any calculus class or could do in any calculus class or DPQ class or anything. E&M, like, this is why I fell in love with E&M and physics in general, is because of the way that E&M sits at the intersection of everything. So it's the intersection of quantum mechanics and therefore chemistry and biology, and at the intersection of Phys 1 and physics and math. Like, it really is the central science. If there's one that's a strongest connection to everything, it really is Phys 2. And I hope that's one of the things that you'll get to appreciate, at least at some level, as we go through, and especially as we leave this class. That's my biggest hope for y'all among many. And I'll say that about a bunch of things, but I think that's truly the biggest hope, the real answer to that. So thanks for hanging out with me through this quick survey of our Unit 3, and I'll chat with you next time as we talk about our waves and such.